You know, every single gadget you own, whether it's your phone or your headphones, they all work because of a few really simple rules and a handful of tiny, tiny components. Today, we're going to pull back the curtain and demystify those fundamentals. Let's dive right in.
So, have you ever wondered how those little parts on a circuit board can do such complex things? I mean, really, how does that work? Well, it all comes down to controlling the flow of electricity with incredible precision. And the secret, you'll see, is surprisingly simple.
Now, just to keep things clear, we're going to focus on direct current, DC, that steady, predictable power you get from a battery. Think of this as a story with a really simple cast. We've got 3 invisible forces that are setting the rules, and 4 key components that are our main players.
Okay, first things first, let's meet the forces. You can think of these as the fundamental rules of the game, the physics that our electronic players have to work with.
First up, we have voltage. And honestly, the best way to think about voltage is just pressure. It's the electrical push that gets electrons all lined up and ready to move. If you don't have any voltage, nothing has any motivation to go anywhere.
Right. So if voltage is the push, then current is the actual movement. It's the flow of electrons through the wire, which we measure in amps, or amps for short. This flow, this is the electricity we're trying to control.
And finally, for every push, there's got to be some pushback, right? That's resistance. It's basically any material's natural tendency to slow down that current. The higher the resistance, which we measure in ohms, the tougher it is for that current to make its way through.
So we've got our push, our flow, and our pushback. But how do they all connect? Well, there's this one beautifully simple rule that governs their entire relationship. It is the absolute foundation of all electronics, Ohm's law.
Ohm's law is basically the glue that holds all this together. It just tells us that if you increase the push, the voltage, you're going to get more flow, more current. Makes sense, right? And if you increase the pushback, the resistance, you're going to get less flow. It's this perfect, predictable relationship.
And this whole profound physical law, it boils down to one simple equation. U equals R times I. Voltage is just resistance multiplied by current. With this one formula, you can predict and control what's happening in almost any basic circuit. It's that powerful.
Okay, so we know the rules of the game. Now let's meet our first player, the resistor. This little guy is the most fundamental component out there, and its whole job is to be the predictable, reliable workhorse of a circuit.
So how does this resistor actually behave? Well, look at this. When we apply 1 volt of push, we get about 22 milliamps of current flowing through it. Now watch what happens when we triple the voltage to 3 volts. Yep, the current pretty much triples too. Double the voltage again to 6 volts, and the current doubles. It's Ohm's law playing out perfectly right in front of us. So here's the key thing to remember about a resistor. The current you get is always directly proportional to the voltage you put in. And, this is important, it doesn't care which way the current is flowing. It's going to provide the same resistance in either direction. Simple, predictable, super useful.
All right, time to meet our specialists, the capacitor and the diode. If the resistor is our predictable workhorse, think of the capacitor as a total roadblock. And the diode, well, the diode is like a really strict bouncer at a club.
First, the capacitor. Now this thing does some really cool stuff when current is changing, but in a steady DC circuit, its job is dead simple. After a tiny little moment where it charges up, it basically just acts like a permanent break in the wire. It completely stops the flow.
And the result? 0. Absolutely 0 amps can get through. Once it's charged up, a capacitor in a DC circuit is just an open switch. It is a total roadblock for direct current. End of story.
Now for our bouncer, the diode. And there is a perfect analogy for this. It's like a one-way check valve for water. You know, the kind that lets water flow through easily in one direction, but if it tries to go backwards, slam, the valve shuts tight.
And that is exactly what a diode does for electricity. In the forward direction, you just have to give it a tiny little opening voltage, and then current can flow right through, no problem. But if you try to send current the other way, the reverse direction, the diode slams the door shut. It's a one-way street for electricity.
Okay, on to our final player, the inductor. And you know what? Its behavior in steady DC might be the most surprising of all. It's basically a shortcut.
Just like the capacitor, inductors get really interesting when the current is changing. But again, when that DC current is steady and stable, an inductor might as well not even be there. It acts just like a simple piece of wire with almost no resistance at all.
You could say it's effectively a short circuit. An inductor lets steady current pass through so easily, it's like you just swapped it out for a plain old wire. For DC, it is the ultimate path of least resistance. So, there we have it, our 3 fundamental forces and our 4 key players. Let's put it all together and look at the final team roster, just to see how each one of these components behaves in a simple DC circuit.
Let's just run through their roles one last time. The resistor, it's our dimmer switch, predictably limiting the current. The capacitor is a brick wall. It blocks current completely. The diode is our one-way door, only letting current flow in a single direction. And the inductor, that's the open highway, a free pass. Getting a handle on these 4 distinct behaviors is truly the first giant leap to understanding how all electronics really work.
Now, everything we talked about today was for steady, direct current. But that brings up a really interesting question, doesn't it? What happens to these components, especially the capacitor and the inductor, when the current is constantly changing direction, like it does in an AC circuit? Well, that's where electronics gets really fun. Thanks for tuning in.